let's continue and let's get back to the textbook. So we are in section 2.1. Last time I was lecturing, I was talking about differentials and how the world would be much nicer if they existed. Today, we're going to talk about how to actually calculate things, how to actually calculate slopes for functions which aren't lines. So geometrically, what's going on? I had a picture something like this on Tuesday where I can approximate rate of change by taking two different points on the graph. And if my coordinate is far away, then the slope that I get is not very accurate. But as I take my 2 points closer and closer together, then I get something that's more accurate. So the idea is that this pink line on the slide is going to have a certain slope, and that's the value of the slope that I would assign to the graph of my function. We would call this pink line a tangent line. So formally, what's going on is that my slope is always calculated as rise over run. The rise here is the difference in the y coordinates. So I'll calculate f of x, and I will calculate f at some other coordinate, call that a for this slide. That's my rise. The run is going to be the difference between x and a. So the formula for the slope is going to be f of x minus f of a divided by x minus a. The problem with this is that my slope calculation is always going to be an approximation. And the quality of that approximation depends on how close or how far apart my points are. So strictly speaking, I've only been able to calculate the slope of these blue secant lines. So secant is a bit of geometry vocab. All that I'm doing is I'm taking two different points on the curve, draw a line between them, and I calculate the slope. The thing that I actually want is called the tangent line. So this slide is saying that the tangent line is the limiting position of the secant line, PQ, as Q approaches P. So we can phrase this in terms of limits, that the tangent line should have its slope equal to the limit of my rise over run formula. So the slope m should be the limit as x approaches a. The formula is f of x minus f of a, all divided by the quantity x minus a. So let's actually work an example. I want to find the equation of the tangent line to a parabola, y equals x squared. And the formula for the tangent requires us to pick a particular xy coordinate. So here we've chosen x equals 1, y also equals 1. So when I calculate the slope, again, the slope is going to be the limit of my slope formula, f of x minus f of 1, all divided by quantity x minus 1. So let's go ahead and write in the formula for y. Let's write in the formula for f of x. This is now the limit as x approaches 1 of x squared minus 1 all divided by quantity x minus 1. Well, hey, that is actually a problem that we can solve now using limits. So I would say I cannot evaluate just by plugging in x equals 1, right? That is not in the domain of this rational function. But I can factor that numerator. Both the numerator and the denominator have a factor of x minus 1, which will cancel. So now I'm just taking the limit of the function x plus 1 as x approaches 1, and that's going to be 2. So this parabola at the x coordinate x equals 1 has a slope of 2, or at least that's the slope of the tangent line at that coordinate.